Hi, today I want to continue our discussion of solutions to linear systems. And today I want to talk about breaking down the general solution into a particular solution and a homogeneous solution. We'll also look at some applications of linear systems in subsequent videos. So this material is primarily from section 1.3 of the text on homogeneous equations. Okay. And I want to use to motivate the discussion, I want to use this example 1.2.3 again that we've looked at previously. The corresponding system of equations, I'll write it down here, is x1 minus 2 x2 minus x3 plus 3x4 is equal to 1, and 2x1 minus 4x2 plus x3 is equal to 5, and the third equation is x1 minus 2x2 plus 2x3 minus 3x4 is equal to 4. So this is we describe this as a 3x4 system, 3 equations and 4 unknowns. We went through the process previously of applying a series of elementary matrix operations, and that enables us to reduce the corresponding augmented matrix to reduced row echelon form. So I'm not going to repeat those steps. Again, they are in the textbook, in that example. Minus 2, 0, and then the constant vector reduces to 2, 1, 0. So this is the reduced row echelon form. And as we said previously, the rows that have leading ones, those ones correspond to what are known as the leading variables. There is no leading variable in this third row, which is all zeros. So again, it is a consistent system of equations, so it does have a general solution. As a matter of fact, it has infinitely many solutions because it has free variables. Okay, so here the lead variables are x1 and x3. Okay. Then the free variables or parameters are therefore the rest, x2 and x4. So we're going to let x2 arbitrarily assign it the parameter s and assign to x4 the parameter t. Now I can use the corresponding system of equations. Of course, this first line corresponds to x1 well, let me write it down. X1 minus 2 times x2, but I'm substituting s for x2, and then plus x4, which is t, is equal to 2. So I can solve for x1. I get 2 plus 2s plus t, and similarly for x3, I get x3 is 1 plus 2t from the second row here. I'm going to arrange the solution as a column vector. we'll call X bar. So I think in the textbook it typically uses bold notation to represent vectors. Can't do bold on a whiteboard, so I'll typically draw a bar over a variable to indicate that it's a vector. And so our solution vector, so our unknown variables are x1, x2, x3, and x4. And these are the elements of our solution vector. Okay, and then I can write that as, so I've got the constant terms for x1, x2 is a free variable, x3 has a constant term, okay, and then x4 is a free variable, so there's no constant term. And then I've got another part of each solution that's multiplied by s. So for x1, sorry, here it is, x1 is 2 plus 2s, and then let me go ahead and write x1 is 2 plus 2s plus t. Okay. x2 is my free variable, so it's just equal to s. Okay. x3 is 1 plus 2t, so there is no s part. And finally, x4 is just equal to my free variable t. Okay. So I can write the solution, and this is what we call the general solution to the system of equations. It includes all possible solutions to the original linear system of equations. So, I can let s and t have any value, and the corresponding x1, x2, x3, and x4 values I can plug into the original system and come up with a solution. I can express the general solution as in the form x is equal to a particular solution plus the homogeneous solution. And we're going to talk a little bit more about the homogeneous solution. Actually, both parts are embedded here in this general solution. So this is the technique that we'll generally use. Work with the original linear system of equations, the non-homogeneous system that includes the constant terms here, reduce it to reduced row echelon form, and then from that I can get the general solution. But I can always express the general solution as a sum of a particular solution and a homogeneous solution, and I want to talk a little bit more about the homogeneous solution today. But I can obtain a particular solution by just assigning any values to s and t. So one particular solution, and probably the most obvious one, is just to let s and t be 0. Okay. So again, this is one solution for x1, x2, x3, and x4, which when substituted into the original system of equations satisfies the system. This would be with s equal to 0 and t equal to 0. Again, that's probably the most obvious particular solution. But another particular solution, if I just let s equal 1 and t equal to 0, I would get, with s equal to 1, I'm going to get 2 plus 2 here, or 4, and 1, 1, and 0. This would be another particular solution. And then actually, the particular solutions plus the homogeneous solution provide the general solution. Okay, I want to look again at the homogeneous part in a little bit more detail. The homogeneous solution is the solution to the corresponding homogeneous system. Okay, and I get the homogeneous system by just setting the constant terms all to 0, okay, or everything to the right of the equal sign when I write the system in standard form equal to 0. Okay. X1 minus 2x2 plus 2x3 minus 3x4 is equal to 0. So this is the corresponding homogeneous system corresponding to our previous example. Again, I can reduce this to reduced row echelon form. The constant portion of the matrix is exactly as before, when we were working with the non-homogeneous system. So the only thing that's different is the corresponding constant column vector. It's going to remain zeros. It initially started with zeros, and so as I, my elementary operations are multiply the row by a constant or add a multiple of another row or swap rows, but I'm always going to have zeros here for the homogeneous system when I reduce that to row echelon form. So again, I identify here the leading ones in each row, get the lead variables x1, x3, free variables x2, which I'm going to assign s, and x4 t, and then so I can solve for the lead variables in terms of my free variables. Now I've got a 0 over here, so the corresponding equation is going to be x1 minus 2s plus t. So solve that for x2, I'll get 2s minus t, and similarly for x3, I'll get from this equation x3 minus 2t is equal to 0, so x3 is going to be equal to 2t. So I can write down the homogeneous solution in this form. 2, 1, 0, 0 plus t times minus 1, 0, 2, 1. Okay. The column vectors here are known as basic solutions. To the homogeneous system. These are not solutions to the original non-homogeneous set of equations. Remember, I have to add in a particular solution in order to get a solution to the original non-homogeneous set of equations. But the basic solutions are, individually, they would satisfy the homogeneous system. There's a basic solution for each free variable, and then a linear combination. This is a linear combination of the basic solutions. Is the homogeneous solution. Basic solutions are not unique. If I multiplied this vector by 2, it would also be a basic solution. It would also satisfy the homogeneous solution. Any scalar multiple of a basic solution is also a basic solution. Okay. But for an m by n system of rank R, and remember rank is the number of leading variables, so this would be a 3 by 4 system, 3 rows, 3 equations, 4 unknowns, and then from the reduced row echelon form we can see that it's of rank 2, Okay, so for an m by n system of rank R, there are n minus R basic solutions. So I said this is 3 by 4, so n is equal to 4. It's rank 2, so we get that there are 2 basic solutions. If R is equal to n, okay, and that's sometimes called a full rank system, the only solution is the trivial solution. Okay, there are 0 basic solutions in that case. So we looked at an example here where there were 2 basic solutions. It was 4 variables, the systems of rank 2, so there are 2 basic solutions. An example of one that's a full rank would be 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and then this is the homogeneous system. Again, it's consistent. I've got all zeros here. Actually, the homogeneous system will always be consistent. But then I have no free variables. My lead variables are x1, x2, and x3. I've only got 3 unknown variables here. And in this case, this is a full rank. N is equal to 3. The rank is equal to 3. The only solution here would be where all x's are equal to 0, and that's called the trivial solution. So note here in this section, I've talked a bit about the homogeneous system and the homogeneous solution. And I know you've probably heard these terms before in your differential equations class, where it's common practice to find a solution to the homogeneous system, the homogeneous differential equation, and then also find a particular solution, and then combine those, add those together to get the general solution. We don't have to do that here with our linear systems. We can work directly with the non-homogeneous system, the original system of equations, apply our Gaussian method, our Gaussian algorithm, our elementary row operations to transform the augmented matrix to reduced row echelon form, and we'll get the complete solution, you know, that consists of particular solution parts and homogeneous solution parts. But I wanted to go through this to introduce some terminology. And you typically won't find the homogeneous solution this way by separately solving the homogeneous system. Instead, you know, we can solve the original system and get the general solution. So I'm going to stop here, and then I'll put up 2 more short videos on a couple of applications that are talked about in the textbook.